Hello guys, I'm gonna try and use these videos to help a little bit because I know that when we need to take notes, then it's very important that you actually see what I'm writing. And last week we had a little bit of a problem with that a couple of times, so I'm gonna try and do this more often. So the concept that we're gonna cover in this short video is phase difference. So phase difference. This has nothing to do with phases as in solid, liquid, and gas phases of matter. This is something completely different, unrelated to that. Phase difference is something that we represent with a letter from the Greek alphabet that looks like this. Sorry, let me draw it again. It looks like this. And the name of that letter is phi. Sometimes you will see it written in some books like this, which is an alternative symbol for phi. But I'm going to stay with the first one because it's easier to draw and also because it's more commonly used. However, in the PDF document that I sent you about oscillations, you will find the other one, the like this one. Okay, but anyway, the concept is phase difference. So last week we introduced our main variables of simple harmonic motion. We introduced period, frequency, amplitude, displacement, and now the one that is joining the club is phi, the phase difference. So what is it exactly? We know that graphs can be represented, oscillations can be represented in different ways, and one of them is drawing the graph of displacement versus time, velocity versus time, or acceleration versus time for one particular type of motion. Last week, and this is just a short parenthesis for those who missed or didn't get that, if you have the displacement time and velocity time and acceleration time graph, if you have your displacement time graph to be something like this, and you want to know what the next graph is, the velocity versus time, the trick we learned was you take this oscillation. Remember, this is one full oscillation up to this point. So you remove a quarter of that, and then if you remove a quarter, you will get this graph only. So that will be your velocity. And if you take the velocity and, in the velocity, this will be one full oscillation, this whole thing, and you remove a quarter of that, that first quarter of the oscillation will be this. So if you remove that, you get only this oscillation. So that will be your acceleration versus time graph. And that was a very nice trick, because by removing that first quarter from displacement, you jump to velocity. By removing that first quarter from velocity, you get to acceleration. And then you can go back by just adding a quarter to acceleration and you get velocity, or by adding a quarter to velocity and then you get displacement. So it's very useful. Now, the reason why I'm emphasizing these graphs is because these graphs actually can be also compared to one another, and that's precisely what phase difference is about. So the concept of phase difference has to do with comparing equivalent graphs for different types of motion or for different situations. It could be the same system, like a mass spring system or a pendulum, whatever you want, but then they are different because the oscillation starts in a different way, right? What we called on Friday the initial conditions. So different sets of initial conditions will give you different graphs. So let's say that we have a situation of simple harmonic motion where this is the graph of displacement versus time. So we know that up to this point we're going to have one period, right? Well, this is the description of the motion. So the concept of phase difference comes handy when you're trying to compare what happened with that oscillation compared to what happened, for example, to this oscillation. So I'm going to make this one my number 2 graph. And number 2 is similar to that one, just that it, it begins like this, right? So the oscillation, it's like like every oscillation, like one of those sine or cosine functions, but it started differently, right? And I'm gonna add yet another one that is going to be my number 3. So this one here is going to be, again, displacement versus time. They're all displacement versus time, by the way, right? But this one is going to be, let's say, something like this. So it's similar, but it starts down here, right? It doesn't start like number 1. It doesn't start right in the origin, but it starts down there. And I don't know, I could even have a fourth one. Sorry, this one is number 3, and I could have a fourth one where the graph of displacement versus time looks something like, let me use a different color. So let's say, I don't know, it looks something like this, right? So it didn't start at the origin, but it started at a maximum point. So how can we compare these 3? Obviously, you could say that you could compare them in terms of the period, right? You can say that one is like, let me just number them to make reference to that more clearly. You could say that number 2, for example, is like number 1, but if you start it half a period later, right? So you don't start here, but you start half a period later, and then you have number 2. You could say that number 3 is 3/4 of a period later. If you take number 1 and you start 1, 2 quarters, 3/4 of a period later, you would start here, and then you have number 3. And you could even say that number 4 is like number 1, but starting 1/4 of a period later. So you don't start down here at the origin in number 1, but up here, right? So you can see how those are related. Now, the thing is that to describe that mathematically, it doesn't make much sense to refer to the period itself, but we will refer to an angle in radians. Now, to understand that, let me just for a while have a small parenthesis here on the sine function, or, well, any of the trigonometric functions, sine or cosine. This sine function is, this is just, I'm going to say this is y-axis, this is x-axis, and this is y equals sine of x, like the very usual shape. Now, in this graph, this point where the sine returns to 0 and the whole cycle begins again in radians is at the value of 2 pi radians, right? So we know that the whole graph will start over after 2 pi radians. After pi radians, it has completed half of its cycle. After pi over 2 radians, it has completed a quarter of its cycle, and it's in its maximum point. And then after 3 pi over 2 radians, it's at the minimum, so it's down here. So you need to remember that if you want to shift things by one full cycle, right? So one full cycle will be 2 pi, right? half a cycle would be pi. Then a quarter of a cycle would be pi over 2, and 3/4 3/4 of a cycle is going to be 3 pi over 2, right? We're not talking about period, we're just talking about the number, the number of radians that this takes. If you wanted to put that in degrees, this would be 360 degrees. This would be obviously 180 degrees. This would be 90 degrees, and this would be 270 degrees, and that's the usual knowledge that we have of the sine function. So when we try to describe how these graphs here are connected, what we do is we describe the phase difference that they have in terms of radians. We don't talk about the period, but we talk about the radians that they have. So in the first one, so this one will be our original one, number 1. So we're going to describe the others in terms of this one. So look at number 2. What is the difference in radians between graph number 1 and graph number 2? Think about it. If you want, pause. Okay, if you thought about it, then you will see that the phase difference between 1 and 2 is half a full cycle, which represents a phase difference of pi over 2, right? Because after pi over 2 radians, if you take graph number 1 and you shift it by pi over 2 radians, you're shifting it by, if you look at this, by pi over, I messed up. I should have said pi, not pi over 2. So sorry about that. So if you look at graph number 1, graph number 2, they are shifted by half a cycle, and half a cycle in radians. If you look at it, half a cycle represents that these two have a shift of pi radians, right? Now let's start fresh with number 3. If you look at number 1 and number 3, what is the phase difference between them? Number 3 is like number 1, but starting down here, right? And if you start down here, how much have you shifted? You have shifted by 3/4 of a cycle, and 3/4 of a cycle represents a phase difference of 3 pi over 2, right? So 3/4 of a cycle is 3 pi over 2, or 270 degrees if you were measuring that angle in degrees. And then what about number 4? Think for a second. Pause the video and think. Okay, if you paused and then you figured out the right answer, you will see that the phase difference for this one is, yes, pi over 2. Because pi over 2 represents a quarter of a period. So everything that you need to keep in mind is this, right? How the sine function behaves, how a full cycle is 2 pi, half a cycle is pi, then a quarter of a cycle or 3/4 of a cycle will be pi over 2 or 3 pi over 2 respectively. So every time you have to compare two graphs, you will describe that not by referring to the period, but by referring to the radians. So all these are radians. 3 pi over 2 radians and pi over 2 radians. What would happen if I take a graph and I draw it with a phase difference of 2 pi radians? Think about it. So probably you got it right. Most likely, if I take graph number 1 and I shift it by a phase difference of 2 pi, that means I'm shifting it by a full cycle. So if I shift that by a full cycle, I'm gonna get exactly the same graph as number 1, because shifting it by a full cycle just doesn't change things, because it will be back where it started. Okay, so this little number phi will tell you how much one graph is different with respect to the other, right? Those are the 4 main phase differences that we have, but we could have something in between. Most likely you will have to deal with these 4, and that's enough for you to know. Okay, thank you very much.